So let's take a look at number 1. For the first question, they want you to traverse the graph in 3 different types of orders: pre-order, post-order, and breadth first search order. So remember, for pre-order, we want to look at the root first, then the left, then the right. Okay? So we're going to start at 9, and remember, in pre-order, we want to return the thing as soon as we see it. So we're going to return the 9 first. So this one is done. And from here, we're going to look at all of our children. So we're going to look at 0, 1, 6, 2, and 7. From here, numerical ties are broken in numerical order. So we're going to look at all of these 5 and say 0 is the smallest one. So we're going to go this way and look at the 0. And we return the 0 once we've looked at it. So this one has already been returned. And then from here, we're going to go back out and look at the rest of the 4 things and say which one is the smallest one, and that would be 1. So we're going to go here, look at the 1, return it. From here, we say, does 1 have children? Yes. So we're going to look at the 6, because that's its only child, and so we have to go this way. And so we look at the 6, return it. And from here, the 6 has 1 child, the 5, so we're going to look at this one and return it. We don't go back and return the 9 because we see that it already has been looked at, and so the only other child that it would have is 5. And so from 5, we see that it has 2 children, 2 and 7. Ties are broken in numerical order, so we're going to have to look at the 2 first. So we traverse this way, look at the 2, and return it. The same concept happens with the 6 and the 5. So here we see that 2 can't go back to 9 because it's already been looked at, and it has no other children besides that. So it has to go back up to the 5, and the 5 has to continue looking for children. And so here, the only other child that we haven't looked at yet is 7. So we're going to go this way and look at the 7. And we know we're done because if we look at the child for 7, we see that it goes back to 9, which is something that we've already looked at and we've already returned. So this is our final answer for pre-order. For post-order, we want to look at the left, the right, and then the root. So here we're going to say left, right, and then the root. So in this case, from the 9, we're going to look at all of our children first and go all the way down until we can't anymore. And from there, we then return it going back up the tree. So here, again, ties are broken in numerical order. So we're going to look at the 0 first. So that's this one. And we see that we can't go any further, so we have to return this one. So this one gets returned first. Going back up in this direction, we see that 9 still has 4 children to look at, so we're going to look at the 1 because that's the next smallest one. So we've looked at the 1, and we see that 1 still has children that it needs to go to. So let's just mark this line to say that we've been here before. And 1 can go down to 6, so we're going to look at that in this order, this directed order. And 6 has to look at 5, so we're going to go this way. And remember, 9 has been looked at already, so we can't go back 9. And 5 has 2 children to look at. We're going to look at the smaller one first, so we're going to go down to 2. From here, we see that 2 can't go back to 9, and 2 has no other children, so we have to return the 2. So 2 gets returned. And from here, we're going to go back up and see if we have any more children. So we're going to go back up to here and look at the 5 again. 5 still has 7 as a child, so we're going to go this way and look at the 7. Because 7 can't have anywhere else to go, because the 9 has been looked at already, we have to return the 7. And from here, since 5 has no other children to look at, then we have to go back up the tree and return everything that we've just looked at. So from here, we're going to return the 5, because that's next. And then we're going to return that 6. So it's here. 1, and finally 9. 1 and 9. And that's our final answer. Alright. In terms of BFS, breadth first search means that we kind of look at it in layers. So what I mean by that is we're going to look at this 9 first, and we return whatever we see. So that's a 9 right here. And then we're going to branch out into the first layer. So in this case, what I mean is we're going to look at the 0, the 1, 6, 2, and 7. Because they are all 1 away from 9, they are considered to be in the first layer. And so, again, ties are broken in numerical order. So we're going to look at these in numerical order and return all of them in numerical order. So we're going to look at 0, 1, 2, 6, and 7. So all of these have thus been returned. From here, we're going to look at the children of all of these nodes, I guess I should say. So in this case, we're going to look at 6, but 6 has already been looked at, so this doesn't really count. We're going to look at the ones that haven't been looked at yet. And so 6 has this 5, and 2 has this 5, and 7 has this 5. And so we're going to return that 5 last, because it's in the second layer. Okay? So let's move on. So let's just review what the invariants of a min heap are. There's 2 of them. Remember that the first one is that we want maximum bushiness. Which means that it has to be a complete tree. And this means that, let's say you have a tree that looks like this. You always have to fill things in from left to right. So if you filled in something that looks like this, then that would be an incomplete tree because you have to fill this left and right node first. So this would be considered a complete tree because you have this and these 2 filled in from left to right, and then you fill in from the leftmost. So you would fill these 2 first, and then if you wanted to fill in the next 2, you would fill it in like that. Okay. The second invariant is that all child nodes have values bigger than its parents. So in this case, what I mean by that is if we have a min heap, all of these children nodes, so this node and this node, have to have values bigger than its parent node over here. So which means that 2 and 3 are both bigger than 1, so this is okay. However, if I had something like 4, 5, and this one were 2 and 4, this would not be a min heap because 2 is not less than 3. Okay, so let's get right into it. So let's just start with our standard min heap. So usually this is like the typical tree that you'll see. So let's see that if traversing this in pre-order will give you an increasing order. So here we want to look at this 1 first, so we're going to return that, and then we return everything on the left hand side, so that's 2, 4, and then everything on this right hand side, so that would be the 5. Okay, and then it would be 3, 6, and 7. So here we clearly see that this is not increasing order. Since there is an example where there's not going to be an increasing order, then this always is out of the question. So the way that we want to look at this is try to find ways that we can arrange it such that it's still a min heap, but things will still appear in increasing order. Since we're looking at the root first, we want to make sure that everything here is still bigger, which means that everything that came in this half, this left half of the tree, was still fine, right? Because this is still in increasing order. And we know that this also is in increasing order. The only problem that we had here was that the 2 sections were not in increasing order. So if we kept the left half of the tree, of the min heap, and changed it so that all the values on the right hand side were bigger than the biggest value on the left hand side. So if we made everything here bigger than 5, then we could have 6, maybe 8, maybe 10. And in this case, if we did a pre-order traversal, it would look like 1, 2, 4, 5. This would be kept the same from the previous tree over here. And then if we went on the right hand side, we would get 6, 8, and 10. And in this case, we see that this is in increasing order. So there are cases where this pre-order traversal can give you an increasing order, so it can't be never. So the answer is sometimes. Okay. Okay. So remember, in order traversal goes left, root, and then right. So here we're going to start with the 4 and return that. So it would be 4, 2, 5, 1, 6, 3, and 7. So here we see that this is clearly not in increasing order, but if we look at it and we try to make a min heap that does have this in order traversal in increasing order, then we see that we can't, because for this case, if we have nodes that are, let's draw this bigger, so we can draw the path that the in order traversal takes. So the in order traversal looks at the very leftmost node, which is this one. And so it starts here, and it goes to the middle, and then to the right, and then to the middle, and then to all of its left, middle, and right nodes, right? So this, it would return something here, 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 and here, right? If you'll follow this arrow this way. So the thing is, this is a parent of these two nodes, which means that this value has to be less than either of these two nodes, right? But if we try to put this in increasing order, that means the middle value is always going to be smaller than the two values around it, which means that this can never have an increasing order traversal, which means it would be this answer, never. So remember, post-order traversal is you want to go all the way down and then return things coming back up. So in this case, your traversal would be 4, 5, 2, 6, 7, 3, and 1. Right? Remember, in a post-order traversal, your root gets returned last, right? So that would be this one. However, in a min heap, the root is always the minimum value, which means that you can never get an increasing order traversal because your minimum value is always going to be the last one. So this one is also never. Okay. Level order traversal, let's just review that one more time. If we had a min heap, a level order traversal will look at the node first and return it, and then look at its children and return both of those because those are both one edge away from the root. So we're going to return 2, 3, and then we're going to look at 2 and 3's children and return all of them in numerical order. So that's 4, 5, 6, and 7. So here we do see that there is a chance where you can get increasing order. So we know that never is not the correct answer. However, let's try to make this change it to a min heap where it fails this case. So we can still have 1 over here. The thing is, we want to make something, because this value gets returned before this value, if we change it so that this value is bigger than this value, then we know that we can't get an increasing order anymore. So if we can keep this side, and then from here we can say, well, I want something that's bigger than 4 but also bigger than 1, which means I can put like 5 here. And then from here I can also put like 10, 12, it doesn't really matter what numbers you put here, because in the end, when you traverse this in a level order traversal, you get 1, 2, 5, and then you come back to 4, 5, 10, and 12. And so here we see that this 5 is in the wrong place, and so we know that always is not the right answer. So in this case, the answer is sometimes. Okay, now looking at the last question, we want to draw a tree with 5 nodes for which the pre-order traversal is the reverse of the in-order traversal. Okay, so remember the pre-order traversal goes root, left, and then right. And your in-order traversal goes left, root, and then right. So if we want these two things to be reversed, and the right thing is always returned after these two things, which happen to be reversed, then that means that in this tree we can't have any right nodes, right? Because if we had these right nodes, then they would be returned after these two, which means that they wouldn't be completely reversed anymore. So that means that we have to have a tree with only left nodes, 3, 4, and has 5 elements, so we're going to go this way. And so let's say that these numbers are 1, 2, 3, 4, and 5. So in this case, if we did a pre-order traversal, we would look at the node first, so we would get 1. And then from here, we would look at all of its left nodes first and return them as we go down. So we get 1, 2, 3, 4, and 5. However, with an in-order traversal, we're going to go all the way down to the left and return all of them coming back towards the root, right? Left root, and then right. So here we're going to look at the 5 first. 4, 3, 2, and 1. And we see that these two are clearly both reversed.